Right now, the tech industry is operating on a single massive assumption that the future of artificial intelligence requires sprawling, centralized server farms. The biggest players are building supercomputers so colossal they require dedicated nuclear power plants to operate. These facilities burn through cash, water for cooling, and electrical grid power. By 2026, global data center power consumption is projected to hit 565 terawatt-hours. To understand the efficiency gap, look at the electricity required for basic internet tasks. A standard Google search uses about 0.3 watt-hours. A single ChatGPT query consumes 2.9 watt-hours, nearly 10 times electricity. Beyond the physical power grid, the centralized model faces a barrier of speed and privacy. Every time you ask a cloud-based AI a question, your device must extract your private data, send it to a server miles away, process it, and send it back. For real-time applications like robotics or instant voice translation, those round-trip network delays are a deal-breaker. Apple realized that the optimal hardware for everyday artificial intelligence could be decentralized, running locally on the devices people already own. While companies like Google and Microsoft spend billions of dollars to maintain their physical infrastructure, they've anchored themselves to a model with inherent physical limitations. This centralized focus allowed Apple the space to quietly develop a different silicon architecture. The shift away from the cloud begins down at the microarchitecture. In 2017, Apple began designing the physical hardware necessary to run machine learning models directly on consumer devices. This wasn't a sudden response to the generative AI boom. In 2017, Apple introduced a neural engine for tasks like image processing and Face ID. By integrating AI hardware early for photography and security, Apple created a specialized foundation that was already in place when larger models emerged. This chart tracks the computing power of the neural engine. It launched in 2017 at 0.6 trillion operations per second, or TOPS. In 7 years, that performance increased to 38 TOPS on their modern 3-nanometer chips, a 63-fold expansion. But high computing power is useless if data cannot reach the processor fast enough. In a typical PC architecture, the CPU and GPU have separate memory pools. Moving data between them creates a physical traffic jam, which limits how fast an AI model can generate response. Apple's unified memory architecture bypasses bottleneck by placing the CPU, GPU, and the neural engine onto a single, shared memory pool, giving every processor instant access simultaneously. The M4 Max chip achieves 546 gigabytes per second of bandwidth. This allows a standard consumer laptop to process massive neural networks using only a few watts of power. Apple engineered the memory bandwidth typically reserved for dedicated server racks into hardware that fits inside a consumer device. Powerful hardware is only half the solution. A 70 billion parameter language model must be physically shrunk down to fit within the memory limits of a phone. To solve this, Apple released an open-source software framework called MLX, which utilizes a technique known as quantization. This diagram shows quantization in practice. By trimming the mathematical weights inside the model, Apple compresses massive software architectures into 4-bit and 3-bit formats. Because of this compression, capable 3 billion parameter language models can now run flawlessly without an internet connection, using less than 2 gigabytes of active RAM. By making inference entirely local, Apple bypasses the need for cloud. This targets the core business model of companies like AWS and Google Cloud, which charge developers to rent server time. Siri features in the Apple Intelligence Interface represent the visible front of a shift in resource economics called zero-cost compute. In the cloud model, scaling AI requires constructing more data centers. Apple is shifting that infrastructure cost onto the hardware their customers have already purchased. Equipping 2 billion active global devices with localized AI chips creates a decentralized computing grid capable of roughly 70 ZOPS. This distributed model provides a computational pool that exceeds any H100 GPU cluster currently housed in a centralized server farm. Independent developers are moving toward local-first applications. This allows them to eliminate up to 80% of back-end API costs while guaranteeing user data privacy through local processing. The ultimate AI supercomputer is distributed across a billion pockets.